Hello guys, and welcome to another calculus video. In this video we're going to be taking on this awesome integral pictured on the screen. We have the integral from 0 to infinity of ln x sine x over x dx. This is an integral from the Cambridge integration bee. I'm blanking on the year, but it doesn't really matter. It's a really cool integral, and we're going to have a lot of fun with it. We're going to solve it using two different methods, so without any further ado, let's go ahead and jump right into the integration. So our first method right here we're going to use is probably the easiest one to spot, because whenever we see ln x in some sort of integral, there's always the thought that the partial derivative with respect to t of x to the t is equal to x to the t ln x. So if we write a function I of t is equal to the integral from 0 to infinity of x to the t sine of x dx, then it's pretty easy to see that I prime of -1, is going to equal our original integral, right? So that's what we're going to try and do in this situation. I'm going to go ahead and actually let this t change this up a little bit, and I'm going to make this I of s and x to the s minus 1. So now we're looking for I prime of 0. And the reason I'm doing this is because this allows us to very easily apply the Mellin transform. And in this case, we're going to use the integral formula, which is provided by Ramanujan's master theorem, and that's that this integral right here is equal to gamma of s times sine of pi over 2s, and this is just using Ramanujan's master theorem. If you want to see the exact derivation of this formula right here, you can go ahead and watch my video on Ramanujan's master theorem. Very incredibly powerful integration technique, and it's perfect for situations like this. So now that we have our integral, all we need to do is differentiate. So we're going to get that I prime of s is equal to the integral from 0 to infinity of x to the s minus 1 ln x sine of x dx, and this is going to be equal to I prime, or gamma prime of s sine of pi over 2s plus pi over 2 gamma of s cosine of pi over 2s. And the problem here is that this gamma s is going to go to infinity, and also this gamma of s is going to go to infinity as we let s go to 0. So we have a bit of an interesting situation here, and we're going to have to actually take this to a limit. So let's go ahead and do that. So we want to let s equal 0, so we're going to let the limit as s goes to 0 of gamma prime of s sine of pi over 2s plus pi over 2 gamma of s cosine of pi over 2s. So the idea here is going to be to abuse the gamma function a little bit here. So first what we're going to do is we know that digamma of x is equal to gamma prime of x over gamma of x, since it's the derivative of the log of the gamma function, which tells us that gamma prime of x is equal to digamma of x times gamma of x. So we're going to use this in our limit right here, and we're going to let this become gamma of s, digamma of s, sine of pi over 2s, plus pi over 2 gamma of s, cosine of pi over 2s. And now we can just factor out that gamma function. So we're going to get the limit as s goes to 0 of gamma of s times digamma of s sine of pi over 2s plus pi over 2 cosine pi over 2s. And we aren't able to completely factor this out yet because this gamma of s, of course, also goes to infinity. But this is easily remedied because we can rewrite gamma of s as gamma of s plus 1 over s, because we know that s gamma of s is equal to gamma of s plus 1. And then we can go ahead and factor this out. So we're going to factor this out, and this is just going to go to 1. So it's not going to end up mattering. And we're going to do the same thing with this digamma of s right here, because we know that digamma of x plus 1 is equal to digamma of x plus 1 over x, I believe. Yeah, plus 1 over x. So we're going to end up with the limit as s goes to 0 of digamma s plus 1 minus 1 over s times sine of pi over 2s plus pi over 2 cosine of pi over 2s all over s. So we're going to go ahead and factor out this bit with the gamma function, and we're going to end up with the limit as s goes to 0, or of the digamma function, sorry, of digamma s plus 1 sine of pi over 2s over s. And this limit is super easy to evaluate since this digamma function is just going to go to negative gamma. And sine of pi over 2s over s, since sine of x over x as x goes to 0 is just 1, when we add that pi over 2, we're just multiplying by pi over 2. So this part of the limit is just going to be negative gamma pi over 2, where gamma is the Euler-Mascheroni constant. Let's go ahead and write that in. And we're still left with a little bit of our limit here, so we're negative gamma pi over 2. And the other part of our limit is the limit as s goes to 0 of, I'm going to write this as pi over 2 s cosine pi over 2s minus sine of pi over 2s over s squared. And I'm actually going to factor out a negative sign here, and you're going to see why in a moment, because this is actually a really cool situation here. This, in case you didn't realize, is actually, on the inside, is the derivative with respect to s of sine of pi over 2s over s. It's just results from the product rule. Wait, I guess I screwed up the negative sign a little bit. Yeah, I guess the negative sign should be outside. It doesn't matter where the negative sign is because sine of pi over 2s, this is an even function. And a great thing about even functions is that the derivative evaluated at 0 is always going to be 0 because that function, whether it's increasing to the right or decreasing, whenever we cross 0, since it's the same on both sides, we're always going to have this flat line. And so the derivative is always equal to 0, so this is just going to go to 0. So overall, the answer to our integral is just a nice, pleasing negative gamma pi over 2. However, we're not done yet because we have another cooler method to evaluate this integral. So one other thing that we can always do to integrals is we can take the Laplace transform with respect to a different variable. The great thing about this is the Laplace transform can be interchanged with an integral because of the properties of the Laplace transform. So I'm going to rewrite this as sine of tx. This is some function of t, and when we take the Laplace transform of this function of t, since we can exchange the integral and the Laplace transform, since the Laplace transform is itself just an integral, we're going to end up with the Laplace transform of sine of tx on the inside, which gives us a polynomial, which is going to be a lot easier to integrate. So we're going to take the Laplace transform, so Laplace transform of I of t. As I said, we're going to interchange the integral in here, and we're only going to take the Laplace transform of this bit. We're going to end up with ln x over x times x over s squared plus x squared dx. Notice that these x's will beautifully cancel out with each other, and we just end up with the integral from 0 to infinity of ln x over s squared plus x squared dx. Let's normalize this integral, so we're going to let x equal s times some variable u. In this case, we're going to be assuming that s is greater than 0, and those are the only values we really need. That means dx is going to be equal to s du. So we're going to end up with s times the integral from 0 to infinity of ln su, which is the same as ln s plus ln u, over s squared times 1 plus u squared. So this s squared can come outside, and we'll just have 1 over s du. Now this part over here with the ln u over 1 plus u squared famously goes to 0. Let's go ahead and prove that real quick. So we have the integral from 0 to infinity of ln u over u squared plus 1. And a really cool way to show that this goes to 0 is we can rewrite this as the integral from 0 to 1 of ln u over u squared plus 1 du plus the integral from 1 to infinity of ln u over u squared plus 1 du. And when we set u to 1 over x right here, we're going to end up with the integral from 1 to infinity of ln, or negative ln x over 1 over x squared plus 1, and then we're multiplying by 1 over x squared because of the differential dx, right? And so these are going to cancel with each other, and we'll just end up with negative ln x over x squared plus 1. And notice that this integral is exactly the same as this, and they're subtracting each other, so they're just going to cancel, and this whole integral goes to 0. So we can just completely ignore this ln u right here. And the other part of it is just going to be the integral from 0 to infinity of ln s over 1 plus u squared, and the ln s doesn't really matter, so we're just going to end with pi over 2 from integrating arctangent times ln s. So that's going to be a pretty easy way to figure out that integral. However, there is a little bit more work that we have to do. So we're going to end up with ln s times pi over 2. And the problem is now we have to take the inverse Laplace transform, and we have a natural log of s. Well, if any of you didn't know, the Laplace transform of ln t actually gives us something in terms of ln s. So let's go ahead and explore that real quick. Let's take the Laplace transform of ln t to figure out how this is going to help us. So the Laplace transform of ln t is going to be the integral from 0 to infinity of ln t times e to the negative st dt. We're going to let st equal u. That means du over s is going to be dt. We'll end up with the integral from 0 to infinity of ln u over s, e to the negative u, and all multiplied by 1 over s du. So we're going to end up with 1 over s times the integral from 0 to infinity of ln u, e to the negative u, minus ln s, e to the negative u du. Now this is an incredibly famous integral, and this just evaluates to negative gamma, where gamma is the Euler-Maccheroni constant, as I call it. Euler-Mascheroni constant, I suppose. And this one is just going to be 1 times ln s, and of course we're subtracting. So we're just going to subtract ln s right here, and that's the Laplace transform of ln t. So let's go ahead and create that in our current problem that we're trying to solve right here. So I'm just going to go ahead and rewrite this as negative pi over 2, negative ln s, and then I'm going to subtract gamma and add gamma back. And then once we expand this all out, we're going to get negative pi over 2 times negative ln s minus gamma all over s. And then we're also going to be subtracting gamma pi over 2s. Now all we need to do is take the inverse Laplace transform, and this is super easy. This is just going to be negative pi over 2 times ln t, as we just showed. And this part is just going to be minus gamma pi over 2, because the inverse Laplace transform of 1 over s is just 1. So this is our answer, and remember that this was our definition for I of t. So when we plug in t equals 1, we are just going to get that this part is going to disappear, and our answer is negative gamma pi over 2. That's it for this video. I hope you guys enjoyed the video and the different methods we showed to resolve this awesome problem. If you want to see more videos like this or have any suggestions, please let me know in the comments. And yeah, that's it. I hope you guys enjoyed the video, and I'll see you next time.